So far in this course, we started off by talking about vector fields, and then we talked about one type of integral over a vector field, a surface integral. So a vector field, remember, tells you the direction and size of the vector at every point. And a surface integral is if you have some surface, how much of the field is going through it. And that turns out to be very useful in electrostatics. But now we're going to go on to a different type of integral in a vector field, which is a line integral. Here's the basic idea. Now, instead of having a surface, we have some line. And each point of the line, say we take that point, we work out, is the electric field or the vector field, whatever it is, pointing in the same direction as the line? In which case it adds to the integral. But let's say over here the vector field is pointing in the opposite direction to the line, it takes away. And if the vector field was at right angles to the line, it has no effect. So it's telling us as we go along the line, is the field going the same way we are on average or going against us? So that's the basic idea of a line integral. Now to try and make this a bit more concrete, let's look at the example of a two-dimensional case, which is slopes. So let's imagine it's a foggy morning and you're in a forest somewhere. You've no idea, you can't see very far because of the fog and the trees, and you want to work out what the scenery is like around there. Or what you can measure locally is what the slope is. So you could get a bob line or something, a ruler or a protractor, and find out if there's a slope. So let's say there's a particular point here, and you might find that the slope is in that direction. So if you drop a ball, it will roll that way. Then you might go over here and find that it goes that way. And over here you might find a steeper slope going that way. Over there you might find a more gentle slope going there. So this way, as you walk around in your foggy forest, at each point you could measure a slope, which is like a vector field, a two-dimensional vector field in this case. And so from building up this field, for example here, it would turn out you look like you have a ridge over there where there seems to be a valley down around here. Now let's say you do go for a walk. So let's say you've got the slope going downhill, gentle, bigger, 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 gentle, small. And let's say you walk along here. You can work out how much your height is changing. What you do is you divide your walk into steps, which might be 1 meter long or something like that. And for each step, you work out the slope, which might be, say, 10%, times the length of that step, delta L, and that gives you the change in height. So if you've got a slope of 10% and you've gone 1 meter, the change in height is 10% of 1 meter or 10 centimeters. And so what you could do, let's say you start here and go up the hill, you might be climbing a mountain here, is for each step you work out how long your horizontal distance of each step times the slope and the horizontal distance of the next step, and you sum them all up. So the sum of the slopes times the elements of length gives you the total change in height. And that's the basic idea of a line integral. What you do is you just go along your line and work out the slope times each element of length, and that will tell you, in this case, the total change in height. Now that's true if you're just going straight opposite the field lines. But let's say, for example, you had a slope that looked like, vector field that looked like this, but you are now walking this way. What's your change of height here? Well, it's fairly obvious you're going parallel to the slope, so you're not actually going up or down. So in this case, there is a vector slope at each point in your line, but it's not making any difference to the height. So in this case, your total change in height is 0. So that seems to indicate that the angle, let's call it theta, between your elements of line and your slope is really important. If you're going straight downhill, the delta H is minus slope times dl. If you're going straight uphill, it's plus. If you're going at right angles, it's 0. That sounds like a cosine theta dependence. And indeed, if you're going, say, somewhere like that, then you're going to be going downhill, but not as much. So in fact, if you're going in some arbitrary direction, the real change in height is going to be s delta L times the cosine of the angle between the two. And that looks like a dot product. So indeed, that's what's the case. The easiest way to write that is we have the slope, which is now a vector, because it's got a magnitude and a direction, dot product the vector delta L. So let's say you're taking a step here, and the slope is like that. You take the dot product of the two, which is the magnitude of one times the magnitude of the other times cosine theta, and that tells you the change in height. Now, of course, if the slope is changing very fast, taking 1 meter step might not be enough. So what you should really do is take infinitesimally small steps. And indeed, that's an integral. So the real change in height is the sum of an infinite number of infinitesimally small steps of s dl. So the delta L's changed to dl because they've become infinitesimally small. So that is a line integral in a two-dimensional surface to work out changes in height.